Question 121. You need to deploy an application on Google Cloud that must run on a Debian Linux environment. The application requires extensive configuration in order to operate correctly. You want to ensure that you can install Debian distribution updates with minimal manual intervention whenever they become available. What should you do? A. Create a Compute Engine instance template using the most recent Debian image. Create an instance from this template, and install and configure the application as part of the startup script. Repeat this process whenever a new Google-managed Debian image becomes available. B. Create a Debian-based Compute Engine instance, install and configure the application, and use OS patch management to install available updates. C. Create an instance with the latest available Debian image. Connect the instance via SSH, and install and configure the application on the instance. Repeat this process whenever a new Google-managed Debian image becomes available. D. Create a Docker container with Debian as the base image. Install and configure the application as part of the Docker image creation process. Host the container on Google Kubernetes Engine and restart the container whenever a new update is available. The correct answer is option B. Create a Debian-based Compute Engine instance, install and configure the application, and use OS patch management to install available updates. Explanation. Using OS patch management on Google Cloud provides an automated way to apply updates to operating systems, including Debian. This option ensures that the application runs in a Debian environment and that OS-level updates are applied with minimal manual intervention. Here is why option B is correct. 1. OS Patch Management. Google Cloud's OS Patch Management supports automated updates for operating systems, ensuring that the instance remains up to date without the need to manually rebuild or reconfigure it. 2. Extensive configuration. Since the application requires extensive configuration, installing it on a single instance ensures that the configuration persists. With OS Patch Management, updates are applied without affecting the existing application setup. 3. Consistency. This approach avoids repetitive steps, such as creating new images or templates, while still keeping the system updated securely. Why not the other options? Option A. Creating a new instance template and repeating the process every time a new Debian image is available introduces significant operational overhead. It requires reinstallation and reconfiguration of the application repeatedly, which is time-consuming. Option C. Manually connecting via SSH for installation and configuration is error-prone and inefficient. It also lacks automation for applying Debian updates, making it less reliable and more labor-intensive. Option D. While using containers with GKE is modern and scalable, it does not align with the requirement to minimize changes to the underlying infrastructure. Containers introduce additional complexity, such as building and managing Docker images, which may not be necessary for a simple application setup. Conclusion. Option B ensures the application can run on a Debian environment with minimal manual intervention. It leverages OS patch management to apply updates securely and efficiently, making it the best solution for this scenario. Question 122. You have an application that runs in Google Kubernetes Engine, GKE. Over the last 2 weeks, customers have reported that a specific part of the application returns errors very frequently. You currently have no logging or monitoring solution enabled on your GKE cluster. You want to diagnose the problem, but you have not been able to replicate the issue. You want to cause minimal disruption to the application. What should you do? A1. Update your GKE cluster to use cloud operations for GKE. 2. Use the GKE monitoring dashboard to investigate logs from affected pods. B1. Create a new GKE cluster with cloud operations for GKE enabled. 2. Migrate the affected pods to the new cluster, and redirect traffic for those pods to the new cluster. 3. Use the GKE monitoring dashboard to investigate logs from affected pods. C1. Update your GKE cluster to use cloud operations for GKE, and deploy Prometheus. 2. Set an alert to trigger whenever the application returns an error. D1. Create a new GKE cluster with cloud operations for GKE enabled, and deploy Prometheus. 2. Migrate the affected pods to the new cluster, and redirect traffic for those pods to the new cluster. 3. Set an alert to trigger whenever the application returns an error. The correct answer is option A. Update your GKE cluster to use cloud operations for GKE. Use the GKE monitoring dashboard to investigate logs from affected pods. Explanation. Enabling cloud operations for GKE, formerly Stackdriver, on your existing GKE cluster is the most efficient and least disruptive way to diagnose the issue. Here's why this approach works best. 1. Minimal disruption. Updating the cluster to use cloud operations for GKE does not disrupt existing workloads. It enables you to collect logs and metrics from the running application without affecting customer traffic or migrating workloads. 2. Immediate diagnosis. Once cloud operations for GKE is enabled, you can access logs and monitoring metrics from affected pods. This allows you to investigate the errors directly without needing to replicate the issue. 3. No need for new infrastructure. Unlike options involving the creation of a new GKE cluster, this approach keeps the existing cluster in place, reducing operational overhead. 4. Integrated monitoring and logging. Cloud operations for GKE provides centralized monitoring and logging, which simplifies the troubleshooting process and allows you to pinpoint the root cause efficiently. Why not the other options? Option B. Creating a new cluster and migrating affected pods introduces unnecessary complexity and disruption. Redirecting traffic to a new cluster can cause downtime and operational overhead. Option C. Deploying Prometheus adds additional tooling, which is unnecessary since cloud operations for GKE already provides robust logging and monitoring. Prometheus is useful for custom metrics but is not required in this scenario. Option D. Similar to option B, creating a new cluster and deploying Prometheus unnecessarily complicates the solution. It is more disruptive and labor-intensive compared to enabling cloud operations on the existing cluster. Conclusion. Option A is the most effective and least disruptive approach to diagnosing the issue. It leverages the native capabilities of cloud operations for GKE to collect logs and metrics, enabling you to investigate the problem directly on the existing cluster. Question 123. You need to deploy a stateful workload on Google Cloud. The workload can scale horizontally, but each instance needs to read and write to the same POSIX file system. At high load, the stateful workload needs to support up to 100 megabytes per second of writes. What should you do? A. Use a persistent disk for each instance. B. Use a regional persistent disk for each instance. C. Create a cloud file store instance and mount it in each instance. D. Create a cloud storage bucket and mount it in each instance using GCSFUs. The correct answer is option C. Create a cloud file store instance and mount it in each instance. Explanation. For a stateful workload that requires a shared POSIX-compliant file system accessible by multiple instances, Cloud File Store is the ideal solution. Here's why. 1. POSIX compliance. Cloud File Store provides a shared file system that supports POSIX semantics, which ensures compatibility with applications requiring features like file locking and consistent metadata updates. 2. Performance requirements. Cloud File Store can handle high write throughput, scaling up to meet the 100 megabytes per second requirement of the workload, depending on the selected tier, example high scale or enterprise tier. 3. Horizontal scalability. Instances can simultaneously mount the Cloud File Store file system, ensuring seamless scaling without needing to duplicate storage. 4. Ease of use. Mounting a Cloud File Store instance is straightforward and integrates well with Compute Engine or GKE instances. Why not the other options? Option A. Use a persistent disk for each instance. Persistent disks are not shared across multiple instances. While they are block storage with high performance, they cannot satisfy the requirement for a shared POSIX-compliant file system. Option B. Use a regional persistent disk for each instance. Regional persistent disks provide redundancy across zones but, like single-zone persistent disks, cannot be mounted by multiple instances simultaneously. Option D. Create a cloud storage bucket and mount it in each instance using GCSFUs. Cloud storage buckets are object storage, not POSIX-compliant file systems. While GCSFUs can provide file system-like access, it does not meet the high write throughput requirement of 100 megabytes per second and lacks full POSIX compliance. Conclusion. Option C is the most appropriate choice. Cloud File Store meets all the requirements, including horizontal scalability, POSIX compliance, and high write throughput. Question 124. Your company has an application deployed on Anthos clusters, formerly Anthos GKE, that is running multiple microservices. The cluster has both Anthos Service Mesh and Anthos Config Management configured. End users inform you that the application is responding very slowly. You want to identify the microservice that is causing the delay. What should you do? A. Use the service mesh visualization in the Cloud Console to inspect the telemetry between the microservices. B. Use Anthos Config Management to create a cluster selector selecting the relevant cluster. On the Google Cloud Console page for Google Kubernetes Engine, view the workloads and filter on the cluster. Inspect the configurations of the filtered workloads. C. Use Anthos Config Management to create a namespace selector selecting the relevant cluster namespace. On the Google Cloud Console page for Google Kubernetes Engine, visit the workloads and filter on the namespace. Inspect the configurations of the filtered workloads. D. Reinstall Istio using the default Istio profile in order to collect request latency. Evaluate the telemetry between the microservices in the Cloud Console. The correct answer is A. Use the service mesh visualization in the Cloud Console to inspect the telemetry between the microservices. Explanation. Anthos Service Mesh provides powerful observability features, including detailed telemetry data for microservices communication. The service mesh visualization in the Google Cloud Console allows you to visually inspect traffic flows, request latencies, and errors between services. This makes it the ideal tool for identifying the microservice causing delays in an application deployed on Anthos clusters. Why this is the correct approach? 1. Telemetry and metrics. Service mesh visualization shows granular metrics, such as request latency and error rates, for traffic between microservices. 2. Real-time insights. It provides real-time and historical data to pinpoint the specific microservice responsible for the delay. 3. Ease of use. The visual representation simplifies troubleshooting by making it easy to trace service-to-service communication paths. Why not the other options? Option B. Use Anthos Config Management to create a cluster selector selecting the relevant cluster. On the Google Cloud Console page for Google Kubernetes Engine, view the workloads and filter on the cluster. Inspect the configurations of the filtered workloads. This approach focuses on inspecting workload configurations, which is not effective for diagnosing latency issues. Configuration details alone do not provide runtime telemetry or traffic flow data between microservices. Option C. Use Anthos Config Management to create a namespace selector selecting the relevant cluster namespace. On the Google Cloud Console page for Google Kubernetes Engine, visit the workloads and filter on the namespace. Inspect the configurations of the filtered workloads. Similar to Option B, this focuses on workload configurations within a namespace but does not address runtime telemetry or traffic metrics. Option D. Reinstall Istio using the default Istio profile in order to collect request latency. Evaluate the telemetry between the microservices in the Cloud Console. Reinstalling Istio is unnecessary and disruptive. Anthos Service Mesh is already installed and configured. The telemetry data is readily available without reinstalling the service mesh. Conclusion. Using the service mesh visualization in the Cloud Console is the most efficient and non-disruptive way to identify the microservice causing delays. It provides detailed telemetry data for troubleshooting and aligns perfectly with the capabilities of Anthos Service Mesh. Question 125. You are working at a financial institution that stores mortgage loan approval documents on cloud storage. Any change to these approval documents must be uploaded as a separate approval file, so you want to ensure that these documents cannot be deleted or overwritten for the next 5 years. What should you do? A. Create a retention policy on the bucket for the duration of 5 years. Create a lock on the retention policy. B. Create the bucket with uniform bucket level access, and grant a service account the role of object writer. Use the service account to upload new files. C. Use a customer-managed key for the encryption of the bucket. Rotate the key after 5 years. D. Create the bucket with fine-grained access control, and grant a service account the role of object writer. Use the service account to upload new files. The correct answer is A. Create a retention policy on the bucket for the duration of 5 years. Create a lock on the retention policy. Explanation. To ensure that documents cannot be deleted or overwritten for a specified period, a retention policy on a cloud storage bucket is the best solution. Once the retention policy is locked, no one can delete or overwrite the files in the bucket until the specified retention period has passed. This satisfies the requirement for regulatory compliance and ensures data immutability. 1. Retention policy. A retention policy defines a minimum retention period during which files cannot be deleted or modified. 2. Retention policy lock. Locking the retention policy ensures that even administrators cannot alter or delete the data until the retention period expires. Why not the other options? Option B. Create the bucket with uniform bucket level access, and grant a service account the role of object writer. Use the service account to upload new files. While this approach limits who can upload files, it does not prevent files from being deleted or overwritten, which fails to meet the requirement. Option C. Use a customer-managed key for the encryption of the bucket. Rotate the key after 5 years. Encryption ensures data security but does not prevent deletions or overwrites. Rotating the key does not address the need to enforce immutability for the specified period. Option D. Create the bucket with fine-grained access control, and grant a service account the role of object writer. Use the service account to upload new files. Similar to option B, this approach only controls who can write files but does not enforce retention or immutability. Conclusion. A retention policy with a lock provides the strongest guarantee that documents cannot be deleted or overwritten for the required 5-year period, aligning with the compliance and operational needs of the financial institution. Question 126. Your team will start developing a new application using microservices architecture on Kubernetes Engine. As part of the development lifecycle, any code change that has been pushed to the remote develop branch on your GitHub repository should be built and tested automatically. When the build and test are successful, the relevant microservice will be deployed automatically in the development environment. You want to ensure that all code deployed in the development environment follows this process. What should you do? A. Have each developer install a pre-commit hook on their workstation that tests the code and builds the container when committing on the development branch. After a successful commit, have the developer deploy the newly built container image on the development cluster. B. Install a post-commit hook on the remote Git repository that tests the code and builds the container when code is pushed to the development branch. After a successful commit, have the developer deploy the newly built container image on the development cluster. C. Create a cloud build trigger based on the development branch that tests the code, builds the container, and stores it in container registry. Create a deployment pipeline that watches for new images and deploys the new image on the development cluster. Ensure only the deployment tool has access to deploy new versions. D. Create a cloud build trigger based on the development branch to build a new container image and store it in container registry. Rely on vulnerability scanning to ensure the code tests succeed. As the final step of the cloud build process, deploy the new container image on the development cluster. Ensure only cloud build has access to deploy new versions. The correct answer is C. Create a cloud build trigger based on the development branch that tests the code, builds the container, and stores it in container registry. Create a deployment pipeline that watches for new images and deploys the new image on the development cluster. Ensure only the deployment tool has access to deploy new versions. Explanation. To ensure that all code changes pushed to the development branch follow a controlled build, test, and deployment process, the best approach is to automate these steps using cloud build and a deployment pipeline. Here's why this is the correct solution. 1. Cloud build trigger. A trigger is set to automatically start a build whenever changes are pushed to the development branch. This ensures that builds happen consistently without manual intervention. 2. Testing and building. The trigger executes the build steps, including running tests and building the container image, ensuring code quality and compatibility. 3. Storing the image. The built container image is stored in container registry, making it easy to manage and deploy. 4. Deployment pipeline. The deployment pipeline automatically watches for new images in container registry and deploys them to the development environment. This ensures a consistent and reliable deployment process. 5. Access control. Restricting deployment access to the deployment tool ensures that no unauthorized code is deployed, maintaining integrity and control. Why not the other options? Option A. Have each developer install a pre-commit hook. This relies on individual developers to handle the build and deployment process manually. It is error-prone, inconsistent, and does not enforce a centralized process, failing to meet the requirement for automated testing and deployment. Option B. Install a post-commit hook. A post-commit hook on the Git repository can trigger builds, but it requires developers to manually deploy the container image. This process lacks centralized control and automation for deployments. Option D. Create a cloud build trigger. Rely on vulnerability scanning. While cloud build triggers and vulnerability scanning are valuable, relying solely on vulnerability scanning for code tests does not cover functional or integration testing. Direct deployment as part of the build process also lacks separation of concerns, making it harder to manage and audit. Conclusion. Option C provides the most robust, automated, and scalable solution for ensuring code changes are tested, built, and deployed to the development environment. It separates the concerns of building and deploying, enforces a centralized process, and maintains control over deployments. Question 127. Your operations team has asked you to help diagnose a performance issue in a production application that runs on Compute Engine. The application is dropping requests that reach it when under heavy load. The process list for affected instances shows a single application process that is consuming all available CPU, and autoscaling has reached the upper limit of instances. There is no abnormal load on any other related systems, including the database. You want to allow production traffic to be served again as quickly as possible. Which action should you recommend? A. Change the autoscaling metric to agent.googleapis.com/memory/%_used. B. Restart the affected instances on a staggered schedule. C. SSH to each instance and restart the application process. D. Increase the maximum number of instances in the autoscaling group. The correct answer is D. Increase the maximum number of instances in the autoscaling group. Explanation. The primary issue here is that the application is consuming all available CPU resources on the existing instances, and the autoscaling group has reached its upper limit. This indicates that the workload requires more compute resources to handle the traffic. The quickest way to restore service and allow production traffic to be served is to increase the maximum number of instances in the autoscaling group. 1. Immediate relief. Increasing the autoscaling limit allows the application to scale out further and distribute the load across additional instances, reducing the CPU load per instance and ensuring requests are handled. 2. No service disruption. This approach does not require restarting instances or processes, which could temporarily disrupt the production environment. 3. Scalable solution. If the application continues to experience high load in the future, the system can automatically scale up to the new maximum limit without manual intervention. Why not the other options? Option A. change the autoscaling metric to agent.googleapis.com/memory/%_used. This is not the root cause of the issue. The problem is related to CPU usage, not memory usage. Changing the autoscaling metric would not address the current overload. Option B, restart the affected instances on a staggered schedule. Restarting instances may temporarily reduce CPU usage, but it introduces service disruption and does not address the root cause of insufficient compute resources. The application would likely face the same issue again under heavy load. Option C, SSH to each instance and restart the application process. Manually restarting the application on each instance is time-consuming and disruptive to production traffic. It is not a scalable or automated solution to the problem. Conclusion: increasing the maximum number of instances in the autoscaling group is the most effective and least disruptive way to handle the current performance issue, ensuring production traffic can be served promptly. Once the immediate issue is resolved, further investigation can be conducted to optimize the application's resource usage and scaling behavior. Question 128. You are implementing the infrastructure for a web service on Google Cloud. The web service needs to receive and store the data from 500,000 requests per second. The data will be queried later in real time, based on exact matches of a known set of attributes. There will be periods where the web service will not receive any requests. The business wants to keep costs low. Which web service platform and database should you use for the application? A. Cloud Run and BigQuery. B. Cloud Run and Cloud Bigtable. C. A Compute Engine Autoscaling Managed Instance Group and BigQuery. D. A Compute Engine Autoscaling Managed Instance Group and Cloud Bigtable. The correct answer is B. Cloud Run and Cloud Bigtable. Explanation. Platform. Cloud Run is a fully managed, serverless platform that can handle high traffic and automatically scale down to zero during idle periods, which is ideal for a workload with fluctuating request rates. It is also cost-effective because you only pay for the resources consumed during active processing. Database. Cloud Bigtable. Cloud Bigtable is a high-performance, low-latency, NoSQL database designed for massive throughput and real-time querying. It is well-suited for storing and querying large-scale data with exact matches on attributes. Its horizontal scalability ensures it can handle the 500,000 requests per second requirement. Why not the other options? Option A. Cloud Run and BigQuery. BigQuery is optimized for analytics and large-scale batch queries but is not designed for real-time querying with exact matches. Additionally, BigQuery has higher query latency, making it unsuitable for real-time applications like this one. Option C. Compute Engine Autoscaling Managed Instance Group and BigQuery. While Compute Engine Autoscaling can handle high traffic, BigQuery is not suitable for real-time querying with exact matches, as mentioned earlier. This combination would result in suboptimal performance and higher costs. Option D. Compute Engine Autoscaling Managed Instance Group and Cloud Bigtable. Although Cloud Bigtable is the right database for this workload, Compute Engine Managed Instance Groups are not as cost-effective as Cloud Run for a service with fluctuating traffic. Compute Engine does not scale to zero during idle periods, leading to higher costs. Conclusion. Using Cloud Run ensures efficient scaling and cost-effectiveness, while Cloud Bigtable provides the necessary performance and real-time querying capabilities. This combination meets the business's requirements for handling 500,000 requests per second, real-time querying, and low costs. Question 129. You are developing an application using different microservices that should remain internal to the cluster. You want to be able to configure each microservice with a specific number of replicas. You also want to be able to address a specific microservice from any other microservice in a uniform way, regardless of the number of replicas the microservice scales to. You need to implement this solution on Google Kubernetes Engine. What should you do? A. Deploy each microservice as a deployment. Expose the deployment in the cluster using a service, and use the service DNS name to address it from other microservices within the cluster. B. Deploy each microservice as a deployment. Expose the deployment in the cluster using an ingress, and use the ingress IP address to address the deployment from other microservices within the cluster. C. Deploy each microservice as a pod. Expose the pod in the cluster using a service, and use the service DNS name to address the microservice from other microservices within the cluster. D. Deploy each microservice as a pod. Expose the pod in the cluster using an ingress, and use the ingress IP address name to address the pod from other microservices within the cluster. The correct answer is A. Deploy each microservice as a deployment. Expose the deployment in the cluster using a service, and use the service DNS name to address it from other microservices within the cluster. Explanation. Deploy each microservice as a deployment. A deployment manages a group of replicas of a pod and ensures high availability by automatically handling scaling and self-healing. This allows you to configure the specific number of replicas for each microservice and easily adjust it as needed. Expose the deployment using a service. A service in Kubernetes provides stable network access to a group of pods, even as pods are dynamically created or destroyed due to scaling or failures. The service will load balance traffic among the pods of a deployment and provides a single DNS name that other microservices can use to communicate with it. Use the service DNS name for communication. Kubernetes automatically assigns DNS names to services, allowing microservices to communicate with each other in a uniform way, regardless of how many replicas are running. This ensures consistent addressing within the cluster. Why not the other options? Option B. Deploy each microservice as a deployment and use an ingress. Ingress is designed for exposing HTTP and HTTPS services externally to the cluster, not for internal communication between microservices. This would add unnecessary complexity and does not align with the requirement to keep the microservices internal. Option C. Deploy each microservice as a pod and use a service. Pods are ephemeral and designed to be managed by higher-level controllers like deployments. Managing individual pods directly does not allow you to scale or ensure availability effectively, making this approach unsuitable for production-grade workloads. Option D. Deploy each microservice as a pod and use an ingress. Similar to option C, directly deploying pods lacks scalability and high availability. Additionally, ingress is unnecessary for internal communication, as it is designed for external access to the cluster. Conclusion. The best solution is to deploy each microservice as a deployment and expose it using a service. This approach provides scalability, high availability, and a uniform DNS-based communication method within the cluster. Question 130. Your company has a networking team and a development team. The development team runs applications on Compute Engine instances that contain sensitive data. The development team requires administrative permissions for Compute Engine. Your company requires all network resources to be managed by the networking team. The development team does not want the networking team to have access to the sensitive data on the instances. What should you do? A1. Create a project with a standalone VPC and assign the network admin role to the networking team. 2. Create a second project with a standalone VPC and assign the compute admin role to the development team. 3. Use Cloud VPN to join the two VPCs. B1. Create a project with a standalone virtual private cloud, VPC, assign the network admin role to the networking team, and assign the compute admin role to the development team. C1. Create a project with a shared VPC and assign the network admin role to the networking team. 2. Create a second project without a VPC, configure it as a shared VPC service project, and assign the compute admin role to the development team. D1. Create a project with a standalone VPC and assign the network admin role to the networking team. 2. Create a second project with a standalone VPC and assign the compute admin role to the development team. 3. Use VPC peering to join the two VPCs. The most correct option is option C. Why option C is the best choice? Shared VPC architecture. This option uses shared VPC, which is the best fit when you need to separate network management from compute management while allowing compute instances to access the network. Shared VPC allows you to have a central network managed by one team, the networking team, and allow other teams, like the development team, to use the network resources without having control over the network itself. Role separation. The network admin role is assigned to the networking team in the host project, giving them control over networking resources. The compute admin role is given to the development team in the service project, giving them the ability to manage compute instances, but not the network configuration. This ensures the team's responsibilities are well separated and the sensitive data on the compute engine instances is protected from network admins. Best fit for the requirement. This approach aligns with the requirement to have the networking team manage all network resources while preventing them from accessing the sensitive data stored on the compute instances. The development team can fully manage the instances, but they cannot touch networking resources. Why not the other options? Option A. Standalone VPCs with Cloud VPN. This introduces VPN connections between two separate VPCs, which is more complex and unnecessary in this case. It requires additional configuration and management, and doesn't provide as clean a separation of roles as shared VPC does. Option B. Standalone VPCs with roles in the same project. This doesn't provide enough separation between network and compute resources. The networking team wouldn't be able to manage the network resources independently of the compute resources. Option D. Standalone VPCs with VPC peering. Similar to option A, it uses VPC peering, which introduces potential security and complexity issues, and also allows the development team to access the network resources, which you want to avoid. Conclusion. Option C is the most correct solution because it follows best practices for role-based access control, network management, and isolation of responsibilities between teams, all while meeting the requirement to keep sensitive data secure from the networking team.